So next up is hydrogenation, and this is going to be the first time in a while that we've seen the alkyne factoring in as well. Hydrogenation, unsurprisingly, is the addition of hydrogen atoms across multiple bonds, and this can be true for both alkenes and alkynes, as we're going to see. To reduce them, what a reduction means is we make more bonds to hydrogen. Alkenes can be hydrogenated to make alkanes because they have no other choice. That's the only place they can go. But alkynes, they have some options. Alkynes can be hydrogenated to both make alkanes and alkenes. And with increasing complexity, both cis and trans analogs. And so we're going to need to deal with a few different types of reagents. Now, the good news is that we're not going to need to know a lot of mechanisms, and so it's mostly just going to be reagents here. There are three types of hydrogenation reactions you should know. The first uses hydrogen and a catalyst that is PD/C. What this is solid carbon, which is actually what's in the tip of your pencil is graphite, with palladium suspended within, typically 10% palladium, and you might see that written sometimes in your textbooks or in your notes. So this uses palladium on carbon as a solid catalyst and hydrogen gas, or H2. Using hydrogen and palladium on carbon leads to the reduction of both alkenes and alkynes all the way down to their most reduced form, which is the alkane. Then there's two other reagents that you need to know. The first is reduction of alkynes to make cis alkenes. This will use something called Lindlar's catalyst. As we're going to see, Lindlar's catalyst is a lead, Pb, poisoned catalyst. And so what this does is it means that the catalyst is active enough to do a single reduction cycle, but not a second. And so Lindlar's catalyst in hydrogen gas will lead to the formation of cis alkenes. Alkynes can also be used to make trans alkenes with a metal and liquid ammonia. The most common metal you're going to see here is going to be sodium, Na. So, hydrogen and palladium on carbon gives us alkanes regardless of where we start. Alkynes have two pathways. Using hydrogen and this poisoned catalyst, Lindlar's catalyst, we can get cis alkenes. Alkynes can also be reduced using metal and liquid ammonia to make trans alkenes. Now let's take a look at the principles of the mechanism to understand the stereochemical outcome. So how does hydrogenation occur, and what does this mean for the stereochemistry? Well, hydrogenation reactions using hydrogen gas and a metal catalyst lead to syn or the same side addition for the stereochemical outcome. I've shown it here from both the alkyne and the alkene. You'll notice here that using palladium on carbon, or in less common examples, platinum oxide, gives the addition of the H2 across the triple bond to give the cis alkene, hydrogen atoms on the same side. And if we are to continue the catalysis, everything would be added syn here. Now you'll notice that the resultant product is not chiral, and so we don't need to worry about that, but it does help to know that we have syn addition, especially when we think about cis versus trans alkenes. Now, since you don't need to worry too much about the stereochemistry, but it helps to understand it, let's take a look at what's going on. You're not going to need to draw the mechanism for this reaction, but it is shown below. The way this chemistry occurs is via something called heterogeneous catalysis, or catalysis that takes place in different phases. The way this works is you have a solid catalyst floating around in solution. This solid catalyst is this precious metal, palladium, platinum, or nickel. And what happens is you bring in hydrogen gas and it bonds to this metal surface and activates the hydrogen. The alkene passes over the surface of this solid catalyst and picks up the hydrogen atoms. And since it does so on a surface, It adds to the same side. The same way if you put your hand down on your desk, everything would be added to the same side. You don't pass your hand partially through the desk and end up with it on opposite sides. So this solid state chemistry is what leads to the cis or syn addition. So let's take one more look at these partial hydrogenations. So the partial hydrogenation is shown here for just one more time. In order to posit the alkene, there are two reactions you should know. We just saw hydrogen and Lindlar's catalyst on the previous slide. And we also remember that metal and liquid ammonia can give the trans alkene, where the most common metals are going to be lithium or sodium. Remember, Lindlar's catalyst is that palladium catalyst that we saw earlier, but it's being poisoned with lead. This poison catalyst means that it can only undergo one reduction cycle. So hydrogenation can be done on alkenes or alkynes. Three reagents to know: hydrogen with palladium on carbon to make alkanes from anything, and hydrogen and Lindlar's catalyst to make cis alkenes from alkynes, and liquid ammonia and a metal to make trans alkenes from alkynes. You do not need to know the mechanism, but you do need to know that this occurs with syn addition when using hydrogen and a metal catalyst.